Okay, I see your screen. That's great. Okay. Hello, everyone. I'm Renee Yager, the Director of Marketing at EPC. Thank you for joining today's webinar, Designing with GaN Power Electronics for Smaller, Lighter, Lower Cost Power Tools, eMobility, and Vacuums. Just a reminder before we start, you can put your questions for the panel in the Q&A box at the bottom of your screen at any time. We will collect these during the presentation and answer them at the end. So now let me introduce our speaker today. Brian Miller is our Field Applications Manager for the Americas for EPC. He has over 30 years of experience in power electronics as a design engineer and as a field application engineer. Brian, thank you so much for joining us today.
Thank you. Let's see, I guess we'll get started now. Q&A. Rick, the agenda for today, going through GaN and consumer products, how they mix together and work together. And then followed by some special topics that come up every so often that might be of interest to you all. Then followed by some short GaN technical news. Then finally a summary. So to kind of set the stage a little bit, why GaN FETs compared to silicon MOSFETs. GaN FETs are smaller, they're more efficient, lower cost total solution, more reliable. They enable higher frequency for system density, and they allow less devices in parallel for higher power. Here's a little overview of some of the parts that the FET range the EPC makes. You can see from 15 volts to 350 volts. The big range is say 40 volts up to 200 volts. That's where most of the EPC GaN FETs are located. Okay, to jump right in, first top vacuums, robotic vacuums, with including mapping by laser, motor drive, and some DC-to-DC example reference designs. So first, the area of lidar and time of flight ranging. There's lots of products that would use this. Today, just robotic vacuums. You see here a little picture of the robot mapping the area. That can be done in different ways. A popular way is to use a laser, the time of flight. So the laser comes from the robotic vacuum, bounces off furniture or the wall and so forth, and the reflected signal is detected by the vacuum. And you can get very accurate measurement of the distance. So as it's shown here on the floor of the house, the vacuum can develop a floor plan of the house. How can GaN FETs help here? The newer advances of GaN FETs is actually GaN IC, is a monolithic IC. An example shown down here with a FET on the right-hand side and the left-hand side, actually a very fast gate driver. This whole thing is only 1 by 1.5 millimeters. The schematic is pretty simple. It's a high-speed gate driver on the left and a single GaN FET on the right. The D pin is where you put a diode. So like a laser diode would go here. GaN FET would turn on and off very quickly, enabling a nice sharp pulse to come out, which would help accuracy of the system. So this uses an example of the 2106 laser driver IC. This particular part is rated for 40 volts and 10 amp pulses. There's other parts we're developing and several on the website. The input can be 3.3 or 5 volt logic level. And it's capable of less than 2 nanosecond pulses, very quick. It could also do 100 megahertz repetition rate. And we also have boards, a demo board or a test board. So you can have a logic input. And over here on the side, there's a place to put your favorite laser. And the driver is so small, well, it's really hard to see even the expanded view, but it's in there too to check the performance for the laser driver. And again, because of the everything in here, it's one piece, and it's a cost-effective solution for this type of situation. Okay, next, motor drive. And this is kind of a general slide. We'll refer to this a few times during the presentation, but on the left, you would see a typical MOSFET kind of motor drive at 20 kilohertz. And you see some kind of zigzags in the sine wave here, discontinuities around 0 and so forth. On the right-hand side, you'll see a GaN-fed motor driver at 100 kilohertz, so 5 times the frequency. Shorter dead time, and there's a reason for the shorter dead time we'll get into also, but you can enable shorter dead time with GaN FETs. So the waveform is smoother, the overall waveform. And looking down, also you see in blue, the input voltage. You have a very nice ramp, and that helps with input EMI. And the input current is much smoother too, versus over here on the left, you see just bigger waveforms, more amplitude, which can cause issues. The issues are EMI, so you might need a filter, and larger capacitors to filter out the 20 kilohertz. Going to 100 kilohertz, you can, in many cases, delete an input filter and have very small ceramic capacitors. So smaller and better quality motor drive. Okay, DC to DC. In some portable vacuums and also other equipment, you'd want a small, efficient DC to DC, especially for less than 30 volt or greater than 30 volt GaN FETs. The GaN FETs are very efficient in that range. Within the last year or so, there have been some new analog and digital controller solutions for GaN FETs. Things like buck controllers, two-phase buck for high current, two-phase boost, and the 4-FET buck boost. For that situation, it seems to be more and more common where the output voltage is sometimes above or sometimes below the input voltage. Here's an example number 1, a very new controller from Analog Devices. Now, this controller is a made-for-GaN buck controller. The input can be from 5 to 100 volts. It can go all the way up to 3 megahertz, but down to 100 kilohertz if you'd like. It's a very nice part because a lot of things are self-contained. You see the 2 FETs here. There's not a lot of external parts. And it has some features to minimize the dead time. So going down a slide, you can see efficiency is very good. Now this one is 2 phases. So if you divide this by 2, say this would be 10 amps for a single phase, you'd be up around 98% efficiency for 28 volts in and 12 volts out. Now it does change with the input voltage. The blue is 54 volts, the gray is 36 volts. But you can see that's very respectable efficiency. I think this particular one is at 500 kilohertz. Second example is from another controller company, Renesas, the ISL 81807. This is a dual phase boost converter. So in a lot of cases, if you have a battery, say the battery is, 6 volts, and you need some higher voltage to run motors or higher voltage to do something else. In audio, you need higher voltage to get enough voltage to run the amplifiers. There's all different types of applications in consumer. But again, this is made for GaN FETs, and it shows this plot is from an APC evaluation board running at 500 kilohertz. Some of the curves are in top view. We look at 36 volts input, 48 volt output, but also 24 volts. You see the efficiency of, looks like 97.5 or so percent. So very good performance out of this also. Go back a slide and also point out very small FETs here that are used. Another example is power tools. Compared to vacuums, power tools would have more power. And the DC-DC would have more power also. Why GaN for motor drives? And again, kind of repeat before, smaller, lighter, higher precision, 6% higher motor system efficiency, and we'll get into details on that later, and less noise. And when you see less noise, you might think, well, okay, that's electric noise. Actually, in addition to that, no, it also includes audible noise. You can have less audible noise. And there's a very nice video on the EPC website that shows how to reduce audible noise using EPC GaN FETs. Okay, this is the same chart as before, but again, as current goes up, you can see all the input amplitudes. And as you have something like a power tool, the filters will get bigger and bigger at 20 kilohertz. And versus 100 kilohertz, or even something higher approaching 100 kilohertz, you can really do well. You can shift from electrolytic capacitors, which have, in many cases, reliability concerns, and they're also big, to something like ceramic capacitors, which are smaller, more easier to deal with, and reliability enhancement. So that's some of the benefits here. You can see some of the offset here. This is not a perfect sine wave. Some of these offsets here, distortions, are actually the cause of audible noise that can come through a motor with a MOSFET drive versus the nice smooth sine wave you get from a GaN FET. Here's some details. On the left, you see an inverter with silicon MOSFETs. On the right, a GaN inverter. Now, there are different conditions, 200 kilohertz versus 100 kilohertz. You can also say 200 nanoseconds versus 14 nanoseconds dead time. You could say that's not fair, but it actually is fair because you can get a reliably 14 nanoseconds dead time with GaN FETs. You can't really do that with MOSFETs due to reverse recovery. So anyway, you can see, let me go down the box. Despite of the 5 times increase in efficiency, in frequency, the efficiency is very close. Actually, a tiny bit less for the GaN inverter. But you keep on going down, and the key points is the total efficiency. Due to torque, due to some mechanical issues with using a non-ideal sine wave versus a more ideal sine wave. You see the total efficiency that gets from the battery into mechanical energy, percentage there, is actually better with the GaN inverter. Shifting a bit to DC-DC higher power evaluation boards. This is something EPC has concentrated on, say, in the last 2 or 3 years. A whole series of boards where these are 2 big inductors, 2 phases, 1 phase here. They can plug into other boards. These have 1 kilowatt per phase. So it's a buck converter, or it can be reversed into a boost converter, but 1 kilowatts per phase. And the typical default configuration is 48 volts to or from 12 volts. They have digital controllers. And again, 2 phases per board, 500 kilohertz. Using one as an example, this one, in the buck mode, you can see approaching almost at 97% at 80 amps output from this 2-phase converter. So very good. Okay, switching again to another one, eMobility, with the topics again of motor drive and DC to DC. Some examples, here's an early one the EPC put together, a little scooter using an inverter. You might have seen this at some of the shows. To the right, showing another, a different FET, which is pretty powerful, only 3.6 milliohms, but yet in only 6.8 square millimeters, this FET. So for things like bicycles and other applications where space is very key, but also efficiency is very key, these can really help out. And there's also FETs that help enable over 96 volts, not just 48 volts, but higher voltage also. Okay, going down a bit here, motor drive, there's some EPC motor drive reference designs you might be interested in. So far, there's 5 boards available now, and there's more coming, including higher power. So looking down at these, they're rated in amps RMS for the brushless DC motor. And these particular ones have input voltage. They kind of top out at, say, well, this one 85 volts, but typically 60 volts. The frequency switching, you can see, goes beyond just 100 kilohertz up to, say, 200 to 250 kilohertz. The question would come up as far as higher current motor drive. Can you parallel eGaN FETs? How does it work? How do you do it? This is a clip from one of the evaluation boards on the previous page. 3 phases. You can see 4 FETs per phase, so it's 2 in parallel on this particular board. All the details are available on the website from the previous part number. But the GaN FETs actually do parallel very well. As temperature goes up, the gate threshold doesn't decrease very much at all. With MOSFETs, that can be a problem. You can have the hottest FET turn on first and turn off last, so it gets even hotter. So you can have the hottest FET get even hotter, and that can cause some problems. That's minimizing GaN FETs. Also, the package is very small for good layout. And also, the gate capacitance on GaN FETs is very low. And what that means is you can take one gate driver and you can drive multiple FETs with one gate driver. By multiple, 4 has been done quite commonly, and more is possible with some design trade-offs, but that's possible also. So we do have one motor driver reference sign that has parallel FETs, and that's the part number right here, 9167HC for high current. And that's the board over here showing 2. And we do have reference designs with even more parallel FETs coming. I think the next one might be 4 parallel FETs per position to get even higher currents. Okay, so that covers current. Then you might ask, well, okay, how about voltage? This is a new series of EPC packaged GaN FETs in small QFNs. Now, so far, the motor drive reference signs we've seen have used 100 volts or less GaN FETs. In the same footprint of the QFN packages here, there's also 150 volts and also 200 volts. So that, for example, if you have a 96-volt battery, you would probably want to use 150 volts. If there's other situations you're worried about transients or something else, up to 200 volts is possible. The current rating on the first one is about 100 amps, and it's also high in the rest of them. So you can have 200 volts at 3.4 milliohms, which is pretty impressive, especially given the size, and down to 1.4 milliohms at 100 volts. So it doesn't take a huge amount of parallel FETs to get some very good current at very good efficiency. Dive in a little bit deeper on 200 volt GaN FETs versus silicon FET. This is a nice little diagram. These are, we think, a one-to-one actual size comparison, or relative size comparison, I should say. Where the first one is 200 volt silicon MOSFET, the next 2 are EPC GaN FETs. Actually, the highest resistance is the silicon MOSFET. The 2 GaN FETs, and this is the picture here of the one I was just discussing on the previous page, a 3x5 millimeter QFN package with a typical RDS on of 3.4 milliohms. You can see other parasitics are very much improved also. The charge on the gate, even though this FET on the right has, well, a little bit more than 1/3 the amount of RDS on, it still has lower gate charge, about 1/3 of the gate charge, which is pretty impressive. Same with gate to drain. Um, it's down there too. The output capacitance is lower. And the reverse recovery is 0 in GaN FETs. That structure that causes that problem isn't there. So again, as the voltage goes up, the advantage of GaN FETs really starts to show in size and parasitics, and that translates into efficiency and helps with design flexibility. Let me go down the page. And now we're going to shift gears a little bit. Those were some previously some look into some functions such as laser driver, various motor drive situations, and also DC-DC. Now a few special topics. These topics come up every so often, so I thought they might be interesting for us to discuss a bit. First one, gate drive for EPCs, GaN FETs. Now just a note, there are various GaN FETs on the market, and they all, not all, but a lot of them have different kinds of gate drive requirements. There's depletion mode GaN FETs, there's some with different gate structures, different voltages for being fully enhanced and so forth. So this talks strictly about the EPCs, eGaN FETs. It's nice and simple. Off is 0 volts. And you might ask, well, how about negative voltage? Would that help turn it off or keep it off or so forth? And no, it's not recommended for EPCs GaN FETs. It turns out a negative voltage would be a waste of effort, kind of waste of money, and it could actually decrease the efficiency. So just simply off voltage of 0 volts is the best. And you want to stay typically less than 0.7 volts. To turn on the GaN FETs, that's also easy, just 5 volts. And the best ideal range for the GaN FETs is from 5 to say 5.2 volts. You're allowed to go a bit higher, but that's about the best range. So again, to recap here, it's almost like 5-volt logic. 0 volts is off and 5 volts is on. The page of, there's a lot of GaN compatible gate drivers. You might ask, well, if it's so simple with 5 volts and 0 volts, why all this here? Well, a few reasons. One's the speed. You want to have a nice fast gate driver. You want to keep under the 6-volt limit on the gate. A lot of these parts have clamps to do such a thing. And they can take the high dV/dt switching that happens in circuits using GaN FETs. So there's single drivers for 1 transistor and half-bridge drivers for a top and bottom FET. The first 3 share a common footprint. Next to are automotive. There's other ones that could go up to 600, 650 volts. And there's some isolated ones also. Okay, changing topics just slightly. The question comes up also with GaN FETs. Are there diodes? Do you have to put an external diode around it? How do you deal with dead time with a GaN FET? And the answer is nice and it's convenient. GaN FETs do conduct in the reverse direction. It's very similar to silicon MOSFETs in the function, except there's no reverse recovery in the GaN in the FETs in the diode mode. The current rating is high because it's the same main channel. It's not a parasitic element. You get the same high current rating. One negative thing, though, is the diode voltage drop is higher. And I have a chart to show that. About 2.5 volts at current. But because there's no reverse recovery, the time you'd spend conducting in the diode mode is very small, typically maybe 10 or 15 nanoseconds or even lower. So the total power loss is small in spite of the higher diode voltage. So in summary, overall GaN advantage in the diode reverse conduction mode and higher total efficiency for GaN. And there's a paper on this too that goes into great detail. If anybody's interested, please send a note or contact Ask a GaN Expert, the link on the last page. Here from a typical data sheet, this is one of the 100-volt QFN packages, reverse drain source. So it's current going from source to drain. The blue is 25 degrees C, so like room temperature. You see the voltage here going up. It's 100 amp part continuous. This is the peak current. So this is really quite a expanded scale. Typical use might be less than 50 amps, so around here so is where you might be. Another topic that comes up often is selecting a GaN FET. There's quite a few and kind of how to get started and what to do because there's conduction loss, there's switching loss, thermal for the size of the package. But EPC does have an online GaN selector tool. And so far it's for buck converters. Here's the link for it. And next page, I'll show a screenshot of it. So here it is. This is the default. It comes up. You can put in whatever frequency you want, whatever maximum junction temperature you want. Input voltage, this one is from 48 volts to 12 volts at 10 amps output. So roughly 120 watts output. You can click on the top FET or the bottom FET. It's already clicked on the top FET. So you can see down here, it gives a lot of information. Resistance, the power due to the conduction, power due to switching. The other one would give power due to dead time and so forth. And in the blue boxes, it ranks there. It's ranked by efficiency, where the top efficiency is at the top and the lower efficiencies are down at the bottom. So this can really help narrow in on a good choice of a GaN FET for a particular situation. And you can change, you could see as the conditions change, like say the current goes up or down, how the choice would be affected also. There's also a calculator on the EPC website I'm not showing for thermals. So you can input thermal conditions and see a thermal output, like the maximum junction temperature under different conditions of heat sink, no heat sink, other conditions. But this can be a good first step to see the total power estimate and do something like put that into a thermal calculator to check a design. And to go back, overall picture of selecting a GaN FET, kind of the process or way it's often done and how to do it a little bit better. One way to do it is to pick a FET that'll work well, meet performance. You can say by performance, efficiency. So say this is efficiency. And Gen 4 FETs, that's a FET series that EPC has had in production for, maybe 4 or 5 years or so. Anyway, you can select a FET and it'll give very good performance. But is that the best FET? Maybe not, because this curve goes up. And you could say, well, I'm not sure I want to spend the extra money for optimal performance, but often cases, smaller FET will actually give better performance. And that's because switching losses. GaN FETs are great for switching loss, but there still is switching loss. The bigger the FET, the more switching loss. So this one is a more optimal design for particular conditions that are shown here of balancing out the conduction loss versus switching loss. If you keep on going and select even smaller one, you can save money and you'll be back where you were at the first place with overall performance. So that looks kind of like the end of the story, but no, GaN keeps on improving. There's all generations all the time. The Gen 5 that's been in production for maybe 2 years now. And using the latest generation, you can then select an even smaller part and have the same performance, more or less, as you had at the beginning, at the start. So if you compare the first FET you chose and the last one, the die size is quite noticeable. And the price difference is just as noticeable. So using something like that kind of idea, like the die size and the previous chart, which I'll go up again, showing a ranked order of the loss of the FETs can really help narrow in on good efficiency and also good cost using the latest EPC GaN FETs. Now, here's just two pieces of GaN technical news to go into a little bit of detail here on some topics many people like. Again, technology evolution. Here's a look at FETs, on resistance on the left and a breakdown voltage at the bottom. An ideal FET would be at the lower right-hand corner here. Silicon MOSFETs have come down from a starting point somewhere over here, and they're almost on top of the theoretical performance limit line. And FETs in the Gen 5 are quite noticeably better, and that gap grows. You can see the gap growing as voltage grows. Still, there's a 300 times difference from the theoretical limit. Now, just a few, like a month ago or so, EPC announced the Gen 6 FETs. They're going through qualification now. Notice how the line moves. They become better for on resistance versus size and so forth. It's 150 times from the GaN limits. Even though it's twice as good, still there's a lot of room for improvement. Now let's look at Gen 6 parts, what that really means. First, a review of Gen 5 performance. Popular FETs, excuse me. The orange is a small FET, the blue is about double the size. So these are some of the most popular FETs out there, 100-volt FETs. This is a buck converter from 48 to 12 at 1 megahertz. This is power loss. Over here, you might be more attuned to this efficiency. So you can see with a small FET, the efficiency is better until you get up to higher currents, in which case the larger FET takes over as the having the best efficiency. Now, something interesting happens when you go to Gen 6 FETs. Because the parasitics are smaller, you basically have the same kind of switching losses with a small FET. But because the RDS on, the conduction loss is reduced, you have even better, basically have the best of both worlds. You have the low current efficiency and high current efficiency actually outdoes both of them. So you have the small package. Here's a little summary over here. So the top line, the big green, shows that you have the same, you have a small package. What it doesn't show is you have, again, basically the same switching loss and better overall RDS on loss, both together. Again, the comparison here, the Gen 6 is more efficient, half the size for the same RDS on. In this particular example, you get 7 amps extra current in the same size before the thermal limit is reached. Less total heat generated and optimized efficiency over the whole range, which is pretty impressive. So a comparison chart showing a silicon MOSFET versus one of the Gen 6 GaN FETs here, which is data sheets on the EPC website. You can see that the resistance is higher in this particular example, but with the switching loss a lot lower, you can get oftentimes with a GaN FET better performance with a higher RDS on FET versus silicon MOSFET. The optimization point might be at a higher RDS on for some of the GaN FETs. That shows up in the calculator. It's really interesting how that works. And again, you see the gate charge quite a bit less and no reverse recovery. And the size quite a bit smaller also. Again, so with the new part, the frequency can be doubled to 1 megahertz. and you can use half the inductance, and that can save space and cost on inductors. And the efficiency is still 1% better than the silicon MOSFET, which would be running at 500 kilohertz. Okay, another piece of GaN news is EPC GaN FETs and packages. Some of you might be already familiar with this, but just a review. So 100 volts, 150 volts, and 200 volts. Either a full-size die in the package or a half-size die in the package. And everything here is pin compatible, so one footprint covers them all. And again, they're all available sampling, and the first one is in production. The rest of them are coming in the coming months and quarters. And again, you look at the low RDS on. Now this is still the Gen 5 part. You can see it doesn't take a whole lot of FETs in parallel to make a very good high current, low loss parallel system. And especially with the gate charge being low, even with such low RDS on, the gate drivers are able to handle that pretty well. So these kind of FETs would be popular for some of the previous motor drive applications, power tools, eMobility, and so forth. The kind of familiar QFN package with the contact that comes around the edge so you can inspect the soldering and so forth. The top has great thermal conduction. As you see over here, it's 0.2 degrees C per watt. It's an exposed die. You get really good conduction out there for heat sinking or heat spreading. The package part is a GaN IC. There's a series of 3 that can do 30 amps, 20 amps, and 15 amps. All in this size package, 3.5 by 5 millimeter. So inside, this is a little bit hard to see, but there's 2 power FETs, the top and the bottom FET, with 2 gate drivers, level shifting, and logic. And the input logic is either 3.3 or 5 volts, and some kind of housekeeping functions inside. So it's very much a self-contained GaN power stage that works well at much higher frequency than you might expect, especially given the voltage rating. Okay, that's it. Again, the little summary here, just EPC team is here to help. There's technical contacts. We have a technical forum, and we also have a cross-reference. If you'd like to take one of your favorite silicon MOSFETs and plug it in and see how a GaN FET might compare a kind of a similar one, you're welcome to do that too. So thank you, everybody.
Thank you, Brian.
Yeah, thank you.
Okay, so we are going to start answering some of the questions that came in while Brian was presenting, and you can still go ahead and put your questions into the Q&A box at the bottom of your screen. So our first question is, what is the load of the 2-phase boost? We can see that the accuracy depends on the output current. So what is the limit to have good accuracy greater than 90%?
Yeah, go back up here.
Okay.
Whoops. Go back up here. It wasn't this one. I think it was up there. I think what he's referring to is the Renaissance boost converter with the high efficiency.
I think so, yeah.
It's the digital one. Here we go. This is the Renaissance boost converter. I think he's asking what the oh yeah, it's not shown. What the tolerance is. I think it's a typical 5% tolerance, or probably less. I think 2% or so on the output. Maybe you could read the question again.
Sure. It says, what is the load of the 2-phase boost? we can see that the accuracy depends on the output current. So what is the limit to have good accuracy greater than 90%? Accuracy or efficiency?
Yeah, it's probably efficiency. So I
Yeah.
think down here, the limitation to get the FET choice is really a big part of this also. The FETs in here were chosen to be able to take up to 5 amps at 48 volts, which is really kind of pushing it. What is that, about 250 watts or so, a little bit less. So this isn't, if you were to use smaller FETs, you could increase the efficiency at light load. So this is really reflects the FETs being used in this reference design. I hope that's a good answer. If not,
Okay.
please write
Right
back.
back in. All right. In example 3, is it easy to put the GaN components in parallel? Is the behavior good? And is the current separated well in each arm?
Yeah, let's cover these in one by one. This
Sure.
particular board has just one FET per position. So there's 2 phases, so there's no paralleling directly on the FET itself on this board. Other boards do have 2 per position. As far as paralleling the phases, yes, it does do well. There's individual sensing on the phases, and the digital controller takes care of that. So yes, there is very good balancing on this, due to the to the good work being done. On this case, EPC and Microchip got together and did this, and yes, it is very well controlled.
Are there any plans to provide advanced simulation models for OrCAD PSpice?
Yes, we do have PSpice models for, I think it's almost every FET that's in production. It should be every FET in production, as well as some that are not quite in production yet. Yeah, there's an EPC model page that has, we have PSpice, LT-Spice, I think we have T-Spice, and there's a few others too we have. So yes, please look at that, or if you can't find it, please write in, and I'd be very glad to help you point you to that page.
Okay. Are the packages shown on slide 36 top cooled?
It can be either. FETs get the maximum amount of power out, do conduct just, go back on again. I guess you could say they're top cooled. What's here and over here that looks like a metal pad, but it's not a metal pad. It's the silicon substrate that's used and the GaN is on the other side. That's how you get such excellent conduction of 0.4 degrees C per watt on the half size, or 0.2 on the full size one. It's not shown here, but there is a good conduction from the junction to the board. Not as good as this, but it is pretty good. So it depends on your design. To maximize the thermal performance, yes, top cooled is the best. In some cases, if you can cool through the board or in-pad vias, then you might be able to have no heat sink and do adequate cooling in a bottom cold situation.
Can you explain more about GaN FET used as a switch in circuit schematic form?
GaN FET used in a switch in schematic form. Really, maybe you mean a series switch, maybe like a load switch. I'm not sure if she or they mean that kind of thing or not. Let's see. I'm going back up to this. Just an example schematic here. I mean, this is a half bridge. I think maybe the question is, can you use it as a switch, like a series switch? Yes, you can. You definitely can. You'd have to have a source of 5 volts over the input along with enough current. GaN FETs take more current than MOSFETs, so you have to make sure you have adequate supply. But yes, they work well in series switches, and they're used there in some applications. There's no minimum frequency for GaN FETs.
Okay. On the integrated half bridge and high side switches, are the gate drivers monolithically integrated in GaN, or is there exposed silicon and are these multi-chip products?
It's a good question. Yeah, it is all monolithic. And let me see if I can back down to that page and skip. Yeah, the whole thing is one GaN chip. There's no silicon gate driver on that or in that package. That whole thing is here we go. So everything that's shown here in the blue box is the total thing. All that is in GaN. One nice thing about GaN is you can have an optimized, say 100-volt FETs, the power FETs, but the little FETs that make up the gate driver, the little FETs for the level shifter and so forth, they can be a lot lower. They could be 20 volts or 10 volts or something like that, just because they can be smaller. It's a lateral device. You can have those together. So it does work out very well.
Okay. So I have a design, my ideal output voltage is around 12 volts. Is there more information about efficiency versus input voltage?
I guess it depends on the particular board. Some of the boards and some of the controllers from different companies, so forth, have graphs at different input voltages. We tend to use 48 volts as an input to 12 volts to kind of show that as a typical situation. If there's a particular one you're looking at, a particular board, yeah, let us know. We might have some curves done. But typically there's no runaway situation where it's good efficiency of 48, but then you get to say 60 volts and it gets bad. You see, like there was one of the charts I showed where the lines are kind of close together. It really does depend on the controller and the FETs in a lot of those cases.
Okay. That was the last of our questions. So if there aren't any more, we can wrap it up. If there are questions after, you can always send them in through Ask a GaN Expert or info@epc-co.com. So thanks everybody for joining us today. The final installment of the GaN for Consumer Application Series is next Wednesday, March 8th. And the topic will be designing with GaN for higher efficiency, smaller, lower cost power banks, battery management, and regulators. More information and registration is available on the website at epc-co.com. And for those of you attending APEC, be sure to stop by and see us in booth 732. Thanks again, Brian, and thanks everybody. Have a great rest of your day.
Thank you all. Bye.
Thanks. Bye.